Let's look at this last example in L'Hopital's rule. So we have a particle that's moving along the y-axis, so it's just moving up and down. So its position at time t is given by this function for t greater than 1. In part A, it asks us to find the velocity of the particle at time t. So recall that velocity is the rate of change of position. So that means they're wanting to find the derivative of this function. All right, so let's find the velocity. And if you notice in the next one, part B, it says the velocity of the particle can be written as v of t equals. So they're actually already handing us the answer. So you can kind of check that as you're doing your work for velocity. So I'm going to label velocity v of t, and I'm going to actually show that I am taking the derivative of our y function. So I'm going to call that y prime of t. All right, so this first one is not L'Hopital's rule. It's just a review of using our derivative rules. Okay, so we have t squared times tangent of 1 over t. So this is overall a product. So I'm going to start approaching this using product rule. So the derivative of the first function, t squared, would be 2t times keep the second function exactly the same. And I like to put that dot for times just to kind of break up that t from the 2t and the tangent. All right, so the derivative of the first times the second plus the first, t squared, times the derivative of the second. So the second function is going to involve chain rule because you have a composition of functions. The outer function's tangent. The derivative of tangent is secant squared of, we're going to keep that inside function the same, times the derivative of the inside function. Now, recall that 1 over t is t to the negative 1 power. So if you want to think about it like that to take the derivative, so that would be times negative t to the negative 2 power. Or it might be helpful to go ahead and rewrite that as 1 over t squared. Okay, now for part A, this would be an acceptable answer on a free response, but I'm going to kind of clean it up a little bit because I want you to see how it turns into the function that's given to us in part B. Okay, so that first expression isn't going to change at all. We're going to have 2t times tangent of 1 over t. Plus, if you notice in the next one, we would have those t squareds that would cancel out. And in fact, that plus would become a subtraction because you're multiplying by that negative 1 over t squared. So we have minus secant squared of 1 over t. Okay, so now it looks like this would be as far as I would go to simplify. However, I want you to look at the expression that they gave us in part B for the function. Notice it's really close, but it's not the same. You've got that tangent of 1 over t, the 2 tangent of 1 over t minus the secant squared. But notice that instead of the 2t, we have dividing by 1 over t. Now, let me explain why that's the case. Why would they write that way in B? And I also want you to understand that multiplying by t, I want you to see that this is in fact the same thing. Okay, multiplying by t is the same as dividing by 1 over t, right? In fact, you would probably simplify this expression as 2t times tangent of 1 over t. So again, why would they want to write it like this in the problem? And the answer to that is in the question that they're actually asking in part B. So they give us the velocity rewritten, and it says find the limit as t approaches infinity. Now, the reason they rewrote this problem for you is if I were to now find the limit as t approaches infinity of the velocity, if we look at it the way that we've written our answer in part A, what we would have, if you were to just kind of evaluate, quote unquote, evaluate at infinity, you would get this would be infinity times, well, 1 over infinity is 0. So you'd get tangent of 0, right? Okay, because you'd have 1 over t as t approaches infinity, that's going to 0. And tangent of 0 is 0. So in this first expression, what you would end up getting is you would get infinity times 0. Now, infinity times 0 is considered an indeterminate format, okay? Because it's people want to say 0 or infinity or something like that. It's actually indeterminate. We don't know what it is. So just like 0 over 0 is indeterminate or infinity over infinity is indeterminate. Now, so what they're leading you to is, where you're wanting to take this limit of this indeterminate form. This is in L'Hopital's rule section. Remember, L'Hopital's rule allows us to take the limit of indeterminate forms, but only in specific types of indeterminate forms. You either have to have 0 over 0 or infinity over infinity. Infinity times 0 doesn't work for L'Hopital's rule. So what the problem has done for you, what part B has done for you, is it's taking the same derivative that you found in part A, and it's putting it in a format that you get that quotient 0 over 0 or infinity over infinity. So what they've done, and I'm going to go ahead and write it in red, is they've taken that t, and instead of multiplying t times tangent of 1 over t, we're dividing by 1 over t. Okay, right? That's the same exact expression. And it doesn't make sense at first why it would be rewritten that way until we are considering taking the limit, because you don't know the limit if it results in 0 times infinity. So now let's think about this. If I now approach infinity with this, so again, we had the 1 over t, as t approaches infinity is approaching 0. So tangent of 0, so we would get tangent of 0 in the numerator over 1 over t, or 0 in the numerator. And then the denominator, we'd get 1 over t. So as t approaches infinity, you'd get 0 in the denominator. Okay, so rewriting it like that gives you the indeterminate form 0 over 0, which then can then be applied for L'Hopital's rule. So that's the motivation why they gave that to you. So it didn't make you have to figure that out on your own. So they handed it to you that way so that it can now apply L'Hopital's rule. Okay, so that's the reason why. So now let's actually answer the question. All right, so in finding the limit as t approaches infinity, using the format that they gave us here, we're going to consider both of these expressions separately. So the first one, we've already kind of talked about that one, you get 0 over 0, and then you have the second one. So what I'm going to do, in order to get full credit on the AP test, you have to kind of split up this numerator and this denominator, okay? So you have to separately show, because you can't just say the limit of that term equals 0 over 0. That's like a bad statement. You cannot say equals 0 over 0, because 0 over 0 is not a legitimate numerical value. So in order to actually do this appropriately, you would show that you're considering the limit as t approaches infinity of that numerator, so the numerator alone, and showing that that's going to equal 0, which we already talked about, because remember that the denominator approaches 0, 1 over approaching infinity is 0, tangent of 0 is 0. And we're also going to talk about that denominator as it approaches infinity. So 1 over t also approaches 0. So now I've shown separately both the numerator and denominator limits equal 0. Therefore, L'Hopital's rule applies. All right. Okay, so that is getting a full point for justification for applying L'Hopital's rule. So now we're going to apply L'Hopital's rule. So if I want to find the limit as t approaches infinity of that velocity function, what I'm going to first show is I'm going to show that I'm going to split up that those two terms. So I'm just going to kind of rewrite this. And again, if this was free response, you want to kind of show as much work as possible. If it was multiple choice, you wouldn't have to show all of this step. All right, so notice what I've done is I've just kind of split up my velocity function into the two terms, and I'm considering those limits separately. So that first one we already talked about up above, that L'Hopital's rule is going to apply to it. So to apply L'Hopital's rule, you're going to keep the limit, and then you're going to take the derivative of the numerator and divide by the derivative of the denominator. So the derivative of the numerator, and something else you could do, you could also take, if you wanted to take this 2 outside the limit, you can definitely do that just to kind of clear that up. So it doesn't matter, you can pull the 2 out or leave it inside. But all right, so if I take the derivative of tangent, you get secant squared, we've already done this, of 1 over t, times, remember, you get negative 1 over t squared. Okay, that's the numerator derivative. We did that up above earlier. Divided by, well, derivative of 1 over t, as we just did, is negative 1 over t squared. So what lovely thing happens is those two things are going to cancel out, which is really nice. Okay, now before I keep going with that one, let's talk about the limit of this other expression. So as t approaches infinity over here, we get 0, again, inside this argument, because as t approaches infinity in the denominator, we would get secant of 0. And so then when you think of secant of 0, or actually I'll go ahead and write that out. So we would get secant squared of 0, and then we'll evaluate that in the next line. Okay. All right, so what I'm now taking the derivative of is actually the same exact thing, correct? I've got, once these 1 over t squareds cancel out, I'm taking the same limit that I just talked about, right? As t goes to infinity, that denominator goes to infinity. So we get secant squared of 0. All right, so we would end up getting 2 secant squared of 0 minus secant squared of 0. And the last thing we do is to evaluate secant of 0. So to evaluate secant, remember that secant is the reciprocal of cosine. So at an angle measure of 0, your cosine value is 1, and then the reciprocal of that is also 1. So secant of 0 is 1, and then 1 squared is just 1. So we end up getting 2 minus 1, or just a value of 1 at the end. All right. So I know that was kind of a long way to approach that, but I just wanted to talk about just that kind of funky looking way that they dealt with that indeterminate form in order to get it in the L'Hopital's rule to apply. All right. And that is it for L'Hopital's rule.